So good morning, everyone. So this first speaker today is Professor Indira Chatterji, and she will continue with her mini course.
Thank you very much. So let me just recall what we discussed the first mini course. That was my view of the world of finitely generated groups. And there's a quote by Gromov that says that any result that's true for any finitely generated group is either trivial or false. So we should keep that in mind when we try to classify finitely generated groups. The best we can do is, put them in some type of bins, and then pick your favorite bin, which could be a single group, and try to prove stuff and understand this particular bin. But trying to understand the whole world of finitely generated group is hopeless. And Genevieve was asking if anybody worked on the zero divisor conjecture. I spent quite a few years on the zero divisor conjecture with no results. And then I think a few famous mathematicians then admitted to me that they actually seem the same. So there are some people who do that sometimes, and Zero divisor conjecture typically is a dangerous one. Sorry? The hardest conjecture, yes. Okay, so this is my word of group. When I discussed it, I made a mistake. I told you I had put SL and Z semidirect product in the wrong bin. It actually has property T as long as n is greater or equal to 3. Out Fn is known for n greater or equal to 4. I don't know what happens for n equal to 3. I couldn't figure out. I have a vague recollection that the answer is no, or maybe it's still open, so I don't really know. I'll leave that on the board, so we'll probably come back to that. So today I'm going to focus on those equivalences. So I already wrote it, but I just rewrite the one I'm going to be focusing on today. The equivalence that G has property T, this is what we discussed with the felt topology, the isolation, and etc. And I understand that if you've never really worked with unitary representation, that was a bit rough, but I hope that you started finding them tractable. This is equivalent to any affine isometric action on a Hilbert space having a fixed point, which is equivalent to any isometric action on a median space having a bounded orbit. If you try to make a strong negation of this, you get that there exists a proper action in a Hilbert space and there exists a proper action in a median space. So this is what's also called Hager property. Or atemanability. And a definition that one can give in terms of unitary action is that the trivial representation is weakly contained in a unitary representation, but not any unitary representation, a representation who has C0 coefficients. So what's the coefficient of a representation? If you take pi, a unitary representation, and you take C eta belonging to H, you're going to define a map. How do you call this map? Okay, phi. C eta going from G to C. You take an element and you map it to the inner product of pi G C with eta. And you want this to be C0. C0 means that you go to 0 at infinity, meaning that each time you have epsilon, for every epsilon greater than 0, there exists a compact which depends on epsilon, such that this is, so you land in C, so you can compute the norm, is less than epsilon for any G outside this compact set. And now that I've told you that, we saw also that that amenable groups didn't have property T because of the regular representation. We had the regular representation, and using Fulner's sequence, we found almost invariant vectors, but if the group is infinite, it has no invariant vectors. So you could think maybe with the rephrasing, that meant that the trivial representation was weakly contained in the regular representation. So let's see why the regular representation has C0 coefficients. If you think of the regular representation, so case, right, case of lambda, the regular representation. So lambda goes from G to the unitary operator of L2G. All right, so at some point I'll mix G and gamma. G is equal to gamma. It's a finely generated group for today. Yes?
I was wondering, in this definition, is it saying there exists these sign in the 8 or?
It's actually for all. Yeah. So, okay, for any two vector, you get a coefficient function, and you want the C0 coefficient for any C0 coefficient. Yeah. Yeah. Thank you. So let's look at the regular representation. Yeah, because of the definition, recall that the definition of like C and eta for the regular representation, so it's L2G, so it's the sum over X in G of psi X, eta X, maybe a bar somewhere. But anyway, think of C and eta, you could think of the Dirac mass at a point. So it's the function that gives 1 at a given point and 0 elsewhere. And this is an orthonormal basis. Right, if C and eta are two Dirac masses at different points, this inner product is going to be 0. And if you take the inner product of a Dirac mass with itself, you get 1. So this is indeed an orthonormal basis. And now why does this regular representation have C0 coefficient? If you pick some Xi or eta, you know, I like to describe them like this. This is a kind of generalization of a Dirac mass, but you're very small at infinity. So that's Xi, that's say it's eta. And then you're going to pick Xi. Xi is another bunk, but it's going to move around with G. And once G gets big, it's going to this is going to be moved off of the main mass of eta. So it's going to become more and more orthogonal. So it's going to become more and more 0. So this is the reason why this has C0 coefficient. Okay, right. Okay, so amenability, if you think of this definition, amenability is anti-T for a straightforward reason, where you just compute the coefficients for the regular representation. Okay, so there are quite a few things I didn't discuss, and I will not discuss, and that we maybe discuss it next time. So there are some equivalent definition using conditionally negative definite kernels. I chose not to talk about it. We have some expert in the room about that. Subhabrata Das and Pardesari Ghosh had a paper, know this stuff really well. So I didn't take this viewpoint. It's not very far from everything I discussed. It was just, I made a choice. And also there is a new characterization. So not discuss, that you might encounter is what we call CND, negative definite kernels, which is just another way of describing Hilbert spaces. And also there is a very important characterization of Ozawa that tells you that you have property T if and only if the Laplacian, which is the element of the group ring that's defined by 1 minus the average over, say, a finite generating set of just the function as you saw in Genevieve's talk. So this gives you an operator on L2, and this, if you have, it was known that if you have property T, this operator gives you a positive operator with a spectral gap in the full C-star algebra. And Ozawa proved that it's equivalent to this being positive in the group ring. And the group ring is just finite stuff. So immediately, this is how property T became checkable by a computer. Because if you're in the full C-star algebra, it's hopeless. You have to take soups and whatnot, so computers cannot do that. But now it became checkable with, in a finite world, and this is how they proved that out Fn had property T. Okay, but today I'm going to say some few more words about median spaces and cat-zero cubical complexes. And then I'll also show you, hopefully, how I'll also hopefully construct some Hilbert spaces and median spaces on which some anti-T groups can act. When I was preparing, I thought, this starts looking like a political party and a political divide. So I hope you're not taking it in that way. Okay, so right. So recall that I have XD, a geodesic metric space. And for a geodesic metric space, I have the interval between 2 points, which is the set of T in X, such that the distance between xt plus distance between ty is equal to the distance between xy. So if you're uniquely geodesic, that's going to be your geodesic. Otherwise, it's all the geodesics. And right, and x is median if for any 3 points the triple intersection of the interval is exactly 1 point, which is, this is called M of x, y, z. It's the median of the 3 points. And so we saw that the main examples, the first obvious example is R. Right. The second example was R2, but I'm putting the L1, which is the taxi cab metric, and you can, it's the metric that you take the difference of the coefficients of your points, and if you do that, you can see that intervals look like this, and if you add a third point, then you can really see your triple intersection. Then another example are trees. Another example is trees. Again, if you have 3 points, the interval is a single geodesic because it's a tree, so they cover each other, and there is a triple intersection here. CAD0 cubical complexes. CAD0 cubical complexes are, before I say that, so if x1, d1 and x2, d2 are median, so is x1 times x2 with the metric d1 plus d2. With just the sum of the metrics. If you did your homework, you read the beginning of the Brights and Heffliger, so you know what CAD0 is. CAD0 means that triangles are thinner than in Euclidean space. If you have two CAD0 space, the product is CAD0 as well, but you can't put this metric. It's not going to be CAD0 with this metric. It's going to be CAD0 with the L2 combination of the metric, the square sum of the metric, but it's the same thing. And here, this is probably the first indication that those are related. That median spaces and Hilbert spaces are related. Hilbert space is the world where you take the square combination, the square sum of your metric, and median is the world where you take the sum. Right. So CAD0 cubical complexes. So what are those? So you take a bunch of cubes. It's a complex that you build out of cubes. So first, let's say first a cube. What is a cube? A cube is the interval 0, 1 to the power n. This is an n-dimensional cube. You see many times people take -1 to 1 to the power n. That's fine too. The advantage of taking -1 to the power n is you automatically have a mid-cube, which is in 0. So that's an n-dimensional cube. So you have a 0-dimensional cube, a 1-dimensional cube. That's a 2-dimensional cube. That's a 3-dimensional cube, and I'll stop here. So my yeah. And what else? Yeah, so that's a cube complex. No, so that's a cube. Cube complex. You glue cubes together isometrically along subcubes. So what's a subcube? A subcube is a cube of lower dimension in the lower dimensional skeleton of your cube. So for instance, if I take this 3-dimensional cube, and I split it somewhere here, this is not a subcube. This is not a subcube. But this face here is going to be a subcube. This is a subcube. Any vertex is a subcube. So gluing isometrically together along subcubes means that you have the illegal gluings. You have some illegal gluings. You're not allowed to do that, for instance. And if you were to do that, you would have to subdivide your whole complex again. If you have a cube complex, you can always subdivide everything. And then you start getting, 4 cubes here and a bunch of cubes here and etc. But yeah, but this, if you don't subdivide, it's an illegal gluing. And so here's some more illegal gluings. You take, you shrink something, or you shrink even more. So those are all illegal gluings, but it's fine for all right. All the rest is fine. So, and then you want it to be cat 0, and this is where the real miracle of cubical complex arise. Yes.
So when you say glue isometrically, what is the metric on the cube? Is it L infinity metric?
Oh no, so no, on the cube I take the L2 metric. Yeah, here I take the L2 metric. Right, so this is, right, so cat 0 is triangles are thinner than in Euclidean space, but then what? You have your cube complex, and how are you going to check that it's cat 0? By checking all the triangle. That's tricky, but this is where the real miracle happens, is you can check it locally with the links. Cat 0 condition is locally checkable on links of vertices. So what's the link of a vertex? So the link is the combinatorial structure of a sphere of radius 1/2. Of a sphere of radius 1/2 around the vertex. And right, so how do you compute the link? For instance, let me just draw here one of my favorite examples of cat 0 cubical complexes. I should have drawn that ahead of time. Okay, so if you kind of see what I'm doing, I'm gluing a 3 cube, and then around this 3 cube, I'm gluing two 2 cubes, and I keep going. And if you're in the back and you don't have your glasses, you might see a trivalent trees. So that's why I don't go too far. And so let's look at the link at this point. So the link is a simplicial complex. It's a simplicial complex where you put a vertex for each edge coming out of your vertex. So the vertices are edges out of your point V. Let's call this vertex V. So here you're going to have 1, 2, 3, 4. And then you put an edge if two vertices correspond to an edge, to edges in a common square. So here I have my 3 points, and so they belong to a common square. They belong to a common square. So I have this, and then I have this. That's it. And then you keep going. So since those 3 belong to a common cube, this is a 3-dimensional cube, you're going to fill your simplex. And you check your CAD0 cubical condition by saying, so links, because check them on links of vertigo, they should be no bygones and flag. Okay, so no bygones means you don't, no bygones means this cannot happen. And if you think about it, how can you get such a link? You get such a link if you take 2 squares and you glue them together isometrically along 2 adjacent subcubes. So you get something like this. And this, if you really think naively in terms of geometry, you have a 90-degree angle. If you go around, you're going to see, you're going to go around and you're going to have 180 degrees, but if you're CAD0, when you go around the point, you need to have at least 360. So that's definitely a non-CAD0 piece that we're avoiding by saying there's no bygone. Flag means that each time, if you see a complete graph of n vertices, then you have an n-1 simplex. So here I saw K3 and I had a 2 simplex. You can remember that as saying every non-simplex contains a non-edge. Each time there's simplex missing, you can't have the full skeleton. Okay, so that's a nice CAD0 cube complex, but it's not yet a median space because it's CAD0, and CAD0 spaces are median only when they're trees. So, but CAD0 spaces are median, that's X, CAD0 space is median if and only if X is a tree. You can think of R2. R2 is really your toy example of a CAD0 space. So R2 with the Euclidean metric, this is not median. Well, because it's uniquely geodesic, so there's no hope of having a triple intersection in a triangle like this. So why did I tell you that CAD0 cube complexes are examples of median spaces? Because I ditched the CAD0 metric and I replaced it with the L1 metric on the cubes, which coincides with the graph theoretical metric of the one skeleton. Yes, question? Sorry? Oh yeah, simply connected. Yes. Yeah, so that's, yeah, thank you. And a cube complex is CAD0, meaning that it admits a CAD0 metric if and only if it's simply connected and links are flags. All links are flag with no bygone. Yeah, and that's really a big difference. If you take a simplicial complex, you're not going to be able to check the cat zero condition with links condition. In fact, if you take a simplicial complex and you try to mimic that, what you're going to get is systolic complexes, for which you have a very rich theory that has many similarities with cat zero cube complexes. Okay, so now, yes? Yes? Yes, an R tree is a median space. Yeah, exactly. So here I have a tree, trees, and R trees. Right, trees are nice cat zero cube complexes. R trees are not cube complexes anymore, but they're still median. Then what else? Yeah, more median spaces. What did I want to say more about median spaces? Yeah.
So when you say the link is not supposed to have a background, but you also said the link is always a simplicial complex.
Yeah, yeah, the link.
So automatically not going to have background.
Right. So.
Why do you need to say that?
Because links are not always simplicial complexes with my definition. Yeah, it's a cell complex. Because if you do that, the link is not going to be simplicial. If you take your two squared that you glue like this, the link you get is not simplicial anymore. Yeah. So either you say the link has to be simplicial and flag, or you say the link has no bygones and is flag. Yeah. Okay, more questions?
Then you probably want to rule out loops.
I rule it out because it's simply connected.
I mean, like the square with two adjacent sides. Loop in the left.
All right, do I need that? So you want to do that? That's my square.
No, square with two arrows.
Like this?
Yeah. So identify those two sides.
Oh, okay. So what should I say? No loop? Or should I just say that the link is simplicial? Okay. No loops. All right. Do nothing funny and you'll be cat zero. Okay. But now if you want to be median, what you need to do, if you take a cat zero, so x a cat zero cube complex, so you change the metric. So you put on it, instead of putting L2 metrics on the cube, then the total induced metric, you're going to put L1 metrics on the cubes, because they're cubes. You have a very nice L1 metric on it. So L1 metric on the cubes, and right, and then the induced metric on the complex. On the whole complex. And that makes the metric then coincides with the graph metric of the one skeleton. So you can now you can ditch all the meat you had on your CAD0 cube complex. You just keep the one skeleton, then you have a graph. And for this graph, the 0 skeleton is going to be a median space for the one skeleton metric. Okay, so those are the first examples of median spaces. Let me just look at more examples. What's interesting in math is that you make a theory, you want few examples, and you're happy you get more examples, but once you have too many examples, it gets disappointing, and this is what's going to happen with median spaces. So, yeah, more examples. So another thing, so now you're going to take X mu, a measure space. So it could be counting measure, it could be a discrete set with a counting measure. Let's say it's nice enough. I'm not going to tell you what, reasonably nice. So what's going to happen? So for instance, the first thing that's median is L1 of X mu. That's not so surprising because it's like a generalization of R2 with the L1 metric. And here you can see that if you take three functions, f, g, h in L1, so I have my three functions, f, g, and say h. So the median is going to be the function that you get in the middle at each time. So you follow here, here, here. I hope I'm doing it correctly. It's like I did before. It's the median of each projection. You know, well, okay, I'm here assuming for the moment that L1 functions are continuous, but what you do it on continuous function, you can find the median in that if your three functions are continuous, then you find this function as a median. So at each time you have a median, and that's your function. So that's so this is a function. So you kind of defined it as the median of f of x, g of x, h of x. And then another example now. I keep my measure space, and I'm going to look at Y, which is the set of subsets in X such that they have finite measure, finite measure subsets of X. So in here you can define a pseudo distance between two sets just by the measure of the symmetric difference. And with this pseudo distance, you get a distance. You can mod out by the elements of distance 0, and you get a distance. So in order for us to see why this is median, we can look at the interval between two sets. I can erase that, right? Yeah, let's erase that. So now I have sets, and let's see why the measurable subsets, the finite measurable subset, form a median space. Why is that? So let's look at the interval between two sets. So the interval between two sets is going to be the set of C and Y, C and Y, such that A intersects B is contained in C, which is contained in A union B. If your sets are not, they don't have an intersection, you're just going to grow from the empty set to both of them. And then you can check that it's indeed correct, because I take here my set C, so this C, this is A, this is B, so let me check that the distance between AB was the distance between BC. So if I look at the distance, no, that's wrong, C. Right. C is my element in the interval. So the distance between A and C, I said it's the symmetric difference. So the distance between A and C is going to be the green part. So the green part is here. So it's whatever is in A but not in C plus whatever is in C but not in A. So this is what you get. And then you look at the other piece, and what the other piece is whatever is in C but not in B, and whatever is in B but not in C. And this is exactly the distance between A and B, because it's the mass of whatever is in A but not in B, and whatever is in B and not in C. And then you can check as an exercise, check that the median between three sets, right? So the median is going to be this pink part. Okay. And then one can show that any median space embeds in a median space like this. So this is where the theory becomes kind of floppy, because here you have like a bunch of really nice and concrete example, but they all belong to that bigger class of example, which is in some sense a bit too general. I mean, which is very general. Okay, yeah. So median spaces were around in the 50s already. People were doing median algebras. They've done quite a lot of work, and then somehow it seemed to. It didn't really die off. It took off really in computer science, and in parts of logic. But it was Martin Roller who did Katsir cube complex and who really popularized. Who did then a bunch of work on median algebra that really revived the subject. Then he quit math, so he never published, for instance, his Habilitationsthesis that has a bunch of foundational theory on median spaces. And also, people were doing median algebra in an algebraic way, so it's less fun than drawing pictures, right? Well, I'll just say that this subject, if not fun enough, then maybe. Okay, right. So, how do you go from median algebra to and Katsir cube complexes to Hilbert spaces? you use, you use walls. So this is a fact that median spaces have a wall structure which is a collection of partitions into, so X is H union H complement, where H and H complements are convex for the metric. Now I have a median space, and what I'm telling you, which is not, so the collection of walls is pretty easy to see on, a CAD0 cube complex, because on a CAD0 cube complex, you have walls in each cube. So here, so now I'm going to think just on the zero skeleton of my complex. It's like a discrete space, and if I cut every cube in two, and I keep the, so here, for instance, I cut my cube, but I keep going with my cut, I'm going to separate my space in two pieces, and this is my collection of walls. On a tree, the walls are pretty easy to see. If you cut an edge in two pieces, you're going to separate your tree in two pieces. That this algorithm separate my CAD0 cube complex is a consequence of CAD0 geometry, and that every median space has a wall structure. So I didn't really, to put a wall structure in a median space, what people had noticed already in the 50s is that, so they had a notion of convex. They didn't have metrics, but they still, even without metrics, they had intervals, they had everything you wish for, except that with a metric, it's more visual. They had already shown that each time you take 2 points, you can find a partition between two convex subsets that separate those 2 points. So the remark is that if you have, for instance, R2 with the L1 metric, your walls are going to be given by all the partition along parallel to the x-axis and all the partition parallel to the y-axis. But if you take anything else, for instance, that's not going to be convex. This is not convex. Because convex means that if I give you any 2 points, the whole interval is contained in it. And here, if you take 2 points, well, the interval is the squared. So it's not going to be contained in either side. So right. So now we know that. Right. So once okay, you have your median space, and now I'm telling you there is this whole collection of walls, and last time I gave you the definition of a wall space. So recall, a wall space structure on X is a collection of partitions but if you have no metric on X, I'm not going to be able to tell you that that set will be convex. So for a wall space, you don't need a metric. All you want is a collection of partition such that for any x, y in x, and a measure on this, and a measure on H, such that the measure on the wall separating x from y is finite. And out of this data, you get a distance, you get a pseudo distance on x. So just imagine it's a distance, or you mod out to get a distance. So if you start with a median space, you had a metric. And if your collection of partitions are convex with complement that's convex, the metric you get is the same as the metric you started with. So so the wall metric, if the walls are convex, the wall metric corresponds to the original metric. Right, and the thing is that some spaces naturally have walls, some spaces are naturally median. So for instance, CAD0 cube complexes are kind of naturally median, and then you produce walls. But then you can ask, if I only have walls, will I recover CAD0 cube complexes or a median space? And the answer is yes. So this is basically how you go from median spaces to space with walls. Yeah. You don't have the, so where? Yeah, so the measure, it's the measure of the set of walls between 2 points. That is finite. So if your walls come from a CAD0 cube complex, you can just count the walls. If you have a finite number of walls between 2 points, you can just count them. If you have an infinite number, you have to be smarter than that, because you need to put a measure, and you need to produce a measure. Right. So for instance, my L1 metric thing, I have too many walls between 2 points, but what I could do is decide that the measure of the number of walls separating 2 points is just the distance, because I have a distance. And in fact, this is how you construct a measure on the collection of walls in a median space. You take all the walls and so you define your measure more or less like you define the Lebesgue measure in R. You start by measuring intervals, and then you extend your measure with a bunch of sets, with intersection and etc.
So does an abstract wall structure include the data of the measure?
Yeah. You need to have a measure and once you have the measure, you can produce a distance. Okay, so now, yeah. So from a wall space, you can construct a median space. So that's the tricky part. If the wall space is discrete, that was Sagiv's work. That's what Sagiv did, although he didn't call them wall space. He called them codimension 1 subgroups. So from the structure of wall space, he has an algorithm, is a way of constructing a cat-zero cube complex, which maybe I'll say a few words if I have time, but that's not totally clear. But if you start with a wall space, the cat-zero cube complex or the median space you get can be quite different because, right. Okay, so let me just go back to property T. Oh no, let me just give you one more example. The example is ARN now with a Euclidean metric. So I told you that's not median, but so not median, but you have a very nice wall structure because you take, okay, let's say Rn is R2. So now I'm going to take as wall structure all possible partitions given by a line. So that's a lot. And I'm going to construct a measure. The measure I'm going to construct, it's kind of here already. Between 2 points, I have a Euclidean distance, so I'm going to say, well, the measure of the measure of the set of walls separating x and y is the distance. They define it like this. So that gives me a measured wall space, and as I told you that you can construct a median space. So I'm going to I embed this into a much bigger median space, who's going to be something like one of the. So in the case of R2, you can really give the embedding. And this now is a median space, but you can see that this, in a sense, is infinite dimensional. And this was something very nice of dimension 2. So wall spaces can potentially be much simpler than median spaces or cat-zero cube complexes. And if you were at Piotr's talk yesterday, he had a Coxeter group with a bunch of walls. But if you try to construct the cat-zero cube complex out of the wall space that Piotr described, you get something that's dimension 4, so you couldn't draw it anymore on the board. And the other example that I want to give is Hn, the hyperbolic space. This has naturally a bunch of Hn minus 1s. Those are your walls. So here you have a bunch of walls like this, and you defined a measure in the same way, and then you have to construct a cat-zero cube, a median space out of that. So then you get something which we don't really know what it is. This is my work with Cornelia Drutu, and so we get a median space, which is some kind of thickening of your H2 or Hn. It's at finite Hausdorff distance, but the walls from the median space correspond. It just extends the wall. You thicken it so that you can really add your medians. And I'm totally running out of time. So let me just go back to property T and AT-menability. With the fact that the free group is AT-menable. So if I want to show that the free group is AT-menable, either I'm happy with the definition of AT-menability that there is a proper action on a median space, then here you have free groups are AT manable or anti-T. Yeah, so either you're happy with this action on a yes. Yeah, Waller lines. And if I take 2 points, I have a set of lines. So I need to put a measure on this set of lines. And I'm going to decide that this measure is the distance between x and y. Exactly. Yeah. And then I have to work to show, no, yeah. I mean, I can do it the other way. If I only have a wall space and no distance, but I have the measure on my wall space, I can define the distance using the measure on the wall space. But if I have a distance and I want to define a measure on the wall space, I'm going to use the distance to define the measure. So, right, so here I have an action on a median space, and how do I get an action on a Hilbert space out of this action? So I get a proper action on L2 of x cross x. So x is the zero skeleton here. So as you remember, maybe or not, if you have an action, alpha action, it had a unitary part and a co-cycle part. So the unitary part, so my Hilbert space is L2 of x cross x. The unitary part, I don't really have a choice, right? Because I'm acting on it, I'm going to permute the elements, so that's a unitary action. And I need to construct a co-cycle. So the way to construct a co-cycle, I'm going to define a co-cycle more or less as a co-boundary, but a co-boundary of an element that's not in the right place. So I'm going to define an F0 minus G F0, where F0, so here I pick a base point, let's say 0, and F0 is the maps that you take 2 points, x and y, and you're going to map it to 1 if x, y points to O, and 0 otherwise. So here I have my tree, here I have my base point, and I'm going to define FO is basically this map. So I have a pair of points. If the pair of points are not adjacent, then it's 0. If they're adjacent and you point to O, then you're going to put 1. So this is clearly not L2. Not in L2 of x cross x. But then when you do F0 minus G F0, so here you have 0, and say here you have G0. Everything cancels. All the pairs of points that you're going to be left are the pairs of points that are on a geodesic between 0 and x0. All the other one pointing here, they're going to, whatever points to the geodesic is going to cancel out. You're only left with this on the geodesic, meaning that this is indeed in L2 of x cross x, and it's a proper cocycle because B of G tends to, B of G, if you compute the norm, the L2 norm of B of G is going to be proportional to the distance between O and GO. So the proper action on the tree will give you that this tends to infinity as G tends to infinity. And you can do exactly the same on a CAD0 cube complex or a median space, and you're going to be left, BG is going to be some type of characteristic function on the half spaces separating O from GO. So again, you have your cocycle that gives you proper action on your Hilbert space. So there's something that I didn't have the chance to do, but you can ask me if you want, is how do you do for an amenable group to construct a proper action? Oh, this says that I still have 3 minutes. Is that true? About 5 minutes? Okay, well, my watch said I didn't have 5 minutes. Okay, all right. Okay, so let me just say a few more words. So, right, so this is how this is the tree case, right? This is how you get proper action on a tree. So this goes back to Hagerup. I think Hagerup really studied the free group. He did a bunch of things. He had a seminal paper on the free group where he did a bunch of stuff. And he also, among all the stuff he proved for free group, some of them gave the Hagerup property. There is another property that stemmed out of this very same paper, which is what I studied in my PhD, which is the rapid decay property. And you can ask me later about that, but it's here, right? But what I'd like to do in the few remaining minutes is show you how the case of amenable groups. So the case of an amenable group is kind of interesting because amenable groups typically do not act on CAD0 cube complexes. Amenable groups, if they're z to the power n, they act on a very nice CAD0 cube complex, which is the cube complex of Zn. But otherwise, they never do, or not properly, because otherwise you're like polynomial growth, you're nilpotent, you get some distortion, and action on CAD0 cube complex don't take distortions. So in general, they don't act on CAD0 cubical complex. So how do you get, and I would like to understand, this tells you that amenable groups act properly on a median space. I'd like to understand the median space they act properly on, but I don't. And but one thing we can say is the Hilbert space they act on. So G amenable acts properly on a Hilbert space. So how do you do that? You take the regular representation, and then you take a countable copy of the regular representation that's going to act on a countable copy of L2. And remember, you had Folder condition. So you write gamma as a union of balls where k goes to infinity. And Folder tells you that for any ball, for any k, there exists uk. You can reformulate formal condition by saying there exists uk such that g uk symmetric difference with k is less than 1 over 2k. So that's a reformulation of Frohner condition, and that's for all g in a ball of radius k. So then you put ck, which is the same almost invariant vector. Yes, you said 5 minutes. And then you check that if you define your cocycle as a direct sum of k lambda g ck minus ck, you can check that this is a cocycle. So the L2 norm is finite, and this is a proper cocycle, so tends to infinity as g tends to infinity. And the question that I'd like to understand is, like, can we have like a geometrical explanation on how the orbit looks like in the corresponding median space? And I'm going to stop here. Thank you very much.
Questions?
Yes. N. Yeah. First you take, it's weird direct sum. The first one is the normal one, and then twice, and then 3 times, and it's going to get bigger, but it's still L2 because of because in fact, it's easy to see that it's L2 because after a point, those are less than 2 to the power k. And so the sum is going to be converged. But the part you left out is going to be bigger and bigger, and is going to grow bigger depending on the size of g. So that's why this thing is going to infinity. Oh yeah, then maybe I'd like to add a reference for property T. So there is if you Google it, you're going to find de la Harpe-Valette and Becca de la Harpe-Valette, which is the standard reference. If you're interested in property T, you should probably read that because it's important to have the vocabulary that other people have. There's also a more accessible reference exactly with this vocabulary is from Gailander and somebody else. I forgot the name. Okay. The title is something like Introduction to Analytic Group Theory. I think Tal Cohen and Gailander, not totally sure, but anyway, Gailander, Introduction to Analytic. So, and this look like a class, and it's not very thick. The problem with the Becca de la Harpe-Valette is very thick, so if you want to read it as an introduction, it's a bit harsh. This one is a nice introduction. Sorry?
The Haggadon's original book about property amenability for free groups.
Yeah.
Has used conditionally
defined
function.
Yeah. The thing is that if you have an action on a Hilbert space, then your cocycle, in fact, is a conditionally negative function. And if you have so in fact, the way we did it with Aglund and Cornelia Drutu, when we were doing the equivalence between median spaces and wall spaces, we really were taking a median space, finding the walls, and etc. And that's and the equivalence between property T. This is how we wrote it up. Now I realize that in fact you could try to do it in a more direct way, taking the definition of property T and and going to conditionally negative definite kernels and trying to go directly. And if you do that, in fact, you will quickly see that everything is in the paper of Robertson Steger from 1996, so way before we did it. So yeah, if that's something that would be nice to actually do, is write the shortest possible proof of the original definition of property T, Kashdan's definition, or the definition for amenability with the representation, and show directly that it's equivalent to either a proper action in a median space or no action in a median space. If you try to do that, you'll see that you very kind of quickly, everything is in there. Yes?
At some point you wrote this function.
Yes.
Which was 1 minus the sum of the generators.
Yeah.
As an operator. Is this greater or equal than 0? What do you mean by that?
Yeah, so that's an operator algebra terminology. When you say that an operator is positive, if you can decompose it as T star T, or a sum of T star T. This is a positive operator. So you're going to say that an operator is positive if it's a sum of this type of operators. Yeah.
Any other questions? So let us thank the speaker again.